This is the second part of Lesson 9 in heat transfer. Lesson 9 focuses on extended surfaces for increasing heat transfer away from a solid-fluid interface. In this part of the lesson, we will derive the governing ordinary differential equation for the temperature distribution along the extended surface. We will then look at the solutions to this differential equation that allow us to calculate the temperature at any location in the extended surface. These solutions will also allow us to calculate the rate of heat transfer through the extended surface. By the end of this lesson, you should be able to derive the governing ordinary differential equation for heat transfer through an extended surface, regardless of what the boundary condition on the surface is. You should also be able to use the solutions to the general form of this equation in order to calculate rates of heat transfer and temperature. This lesson is a bit longer than prior lessons, and you may wish to pause halfway through and take a break. On with the lesson.
So increasing area is the name of the game for extended surfaces. So we need to think about how we can model these things so that we know how to make design choices, right? For designing heat sinks, or we're going to start with a single fin. We're going to call it a pin fin, right? But be thinking in the end, our end game here is to ultimately model an entire heat sink system, all right? Okay, so we start by drawing a single fin. I'm going to draw it so you have a chance to draw it in your notes too. So we're going to think about what's called a pin fin, okay, which is a long cylindrical looking thing. It's extending off of the interface that we are trying to keep cool. Okay, so here is that interface. And we want to label some important things here. So I want to label, we want to establish a set of coordinates. So there's a radial direction because it's a cylindrical system. And there's an axial direction, which we'll label with X. And this over here at the base we'll call X equals 0, and we'll call the tip, okay, this is called the tip of the fin or the tip of the extended surface. That's at X equal L. So this fin has some length, okay, that we have to take advantage, we have to recognize. And it also has some diameter D. So I'll do that, I'll draw, this is a diameter D, right, which is 2 times the radius. And then there is some fluid, right, that's around the heat sink and flowing over this thin surface. It could be forced flow, like in our radiators in the room, right? When the fan kicks on, it blows air over the radiator surface. Or it could be some natural convection that's happening as well. In either case, we're characterizing it with a convection coefficient and some fluid temperature T infinity. The base, what we're going to call the base temperature, is the temperature over here. And this is the temperature at X equals 0. And we're going to say it's TB for base temperature. All right, so in looking at these systems, we're going to make some assumptions, right? And here's what the assumptions are going to be. We're going to say, 1, that there is no delta T in the radial direction. I'm going to tell you that's the one we're going to have to check, okay? The other is that the thermal conductivity is equal to a constant, as is the convection coefficient, right? Just single numbers. We're going to say that we're going to assume that the heat sinks are operating at steady state, and that there is no thermal energy generation in the inside of the heat sink at all. Okay, so you look at this list and it satisfies most of the most of the requirements for the thermal circuit, yeah. But the one that really is tricky is the 1D. So we definitely, with this no delta T in the radial direction, the conduction heat transfer we're going to say is one-dimensional along the axis, but there is some convection heat transfer in the other direction. Yeah, so in the radial direction, there is convection heat transfer off of the cylindrical surface of the pin fin. So I actually call this problem a 1.5D heat transfer problem, okay, which you think a half a dimension is kind of weird, but what I'm trying to remind myself of is that the heat transfer in the radial direction is just convection, right? Conduction is not important inside of the pin fin. It's only the convection on the surface. So we really need a way to check that, right? How do we make sure that this is true, right? So how is this true, or how can we know if this is true? And so we're going to have, I'll show you how we do that. Okay. So if you think of a cross section of the pin, right, which is the part of the thing sticking away from the surface, and we look at the temperature at the center line. So I'm going to label two temperatures. There's a temperature here at the center of the pin fin. And we're going to look also and think about the surface temperature, Ts, and the temperature T infinity far away in the fluid that's flowing over this thing. Right, so there's some fluid, right, we said, that's flowing over the surface of this heat sink fin, characterized by some H, and has some T infinity. The fin has some radius R. Okay. So if we think about the relationship between the center line temperature, the surface temperature, and the fluid temperature, if we're saying that there is no important gradient of temperature in the radial direction in the fin, we can do that by comparing differences between the center line and surface temperature and the surface temperature and the fluid temperature. So we're going to do this, try to figure out how to work out quantifying this ratio, which is the difference between the center line temperature and the surface temperature, and the difference between the surface temperature and the fluid temperature. So if this ratio is a lot smaller than 1, it means that the difference between the surface temperature and the fluid temperature is large compared to the difference between the center line temperature and the surface temperature. Or in other words, that there's not a large temperature variation between the center and the surface. Yeah. And then we're good, I guess. So if this, then dt dr is approximately 0. So how can we work out something for this ratio? We're going to do it by applying a surface energy balance at the surface of the fin. Okay, so if I look at an energy balance at the surface, it's good to draw the control system. So we're looking at just, kind of breaking out and looking just at, right, what's happening at this interface. And we're talking about, we have some conduction on the inside that's going up to that interface, right? And then on the outside, this is convection. But the surface energy balance says that those two things must be equal, right? Because whatever conduction goes into the surface has to come back out as convection into the fluid. So what we have then is the conduction is like minus K dt dr at this outer surface at R equal R, and that's got to equal the convection there. Okay. So what we're going to do to try to get a sense of this ratio is we're going to make a really big approximation for this dt dr. We're going to say dt dr at R equal R is approximately minus, we're just going to take the difference between the center line temperature and the surface temperature and divide it by R and say, let's just pretend that it's linear. But we know it's not linear, but right, which hopefully I convinced you of that on Wednesday, that it's not linear, but we're just going to say that it's linear for the purposes of doing this scaling, right? Because it's going to make it easy for us to work out the balance. So if I make that substitution, I have K, the minus cancels with the minus, right? Times T center line minus TS over R is approximately H times TS minus T infinity. And now we're going to just solve for our ratio. So we're going to put the T center line minus TS and the TS over TS minus T infinity on one side and look at everything else that comes out on the other side. So we have T center line minus TS over TS minus T infinity. That's our ratio. All I did was move the TS minus T infinity over. We're saying that's approximately equal then to HR over K. So you see, I can evaluate this quantity HR over K just from information what I know about the pin fin. I know the material, so I know its thermal conductivity. I know its size, and I know something about the convection. And just from looking at this ratio, then I can say something about whether or not the temperature gradient inside of the fin in the radial direction is important. This dimensionless ratio is called the BO number. It's French, a French name. Okay, so this is BO, not BIOT. It's BO number. And it's really important for us, okay? It's how we're gonna make sure that our assumption that there's no radial temperature gradient is true. So just to write that down, if the BO number is much, much less than 1, then we can neglect gradients in the radial direction. But if the BO number is on the order of 1 or greater than 1, okay, then the DTDR is not negligible. We have to account for it. And physically, the BO number represents a ratio, actually, of resistance to heat transfer by conduction and convection. And it says that the most of the resistance to heat transfer in the radial direction is by convection, right? So there's not a lot of resistance for the conduction, and so the temperature smooths out and is the same everywhere. Conduction is fast relative to the convection, and so the temperature gets smoothed out because the thermal energy moves quickly in the radial direction relative to how it moves from the solid to the fluid. Any questions on that or what the BO number is? You can apply it in more than just this case. Anytime you want to say, is there an important conduction problem, you can evaluate this number where you replace the length scale R with something else. So it could be the thickness of the plane wall, for example. You could put in L, and if HL over K is really, really small, it's probably not an important temperature variation in the wall, right? It's all at the surface, between the surface and the fluid. Okay, so then we go back to our picture, and what I want you to do, I've redrawn it here with, not my sloppy handwork. I want you to, as practice, we know that we can't apply the thermal circuit, so we have to derive the governing differential equation for temperature in the fin, in the heat sink. So this is a great opportunity for you to practice this skill, right? You've seen it now in class, and then you had the homework assignment due Wednesday. So see if you can define a small differential control volume in the fin, right? Set up that differential control volume and work out and get down to the governing differential equation, right, for the temperature. So the goal is to derive the differential equation that will lead to the temperature distribution and the heat transfer, right, in the fin. So I'm going to give you a chance to try to set it up on your own.
Now, what I would like you to do is pause the video and write down an answer to the question.
Let me just go through the setup because I think many of you are still kind of having a hard time seeing the starting place. And if you can get the starting place, then you can follow the steps. Step one is always to think about the differential control volume and think through the problem, like what's happening. So we have conduction along the axis of the fin and I have convection in the radial direction. So I need it to be differential in the x direction. So I'm thinking about taking a tiny slice, right, of this fin out. Right, this thing is going to be a tiny slice. It's got to be differential in the direction in which there's conduction. It doesn't have to be differential in the radial direction because there's no conduction in that direction. There's only convection. So I like to draw this thing on its side. So like I'm looking at it from its side this way. Okay. And it's a little tiny slice, and I do these little dashed lines in the direction that it's differential. Right, so it's dx this way, and it's d this way. That's the geometry. And then I think through where's the heat transfer. So there's conduction along the axis of the fin. So there's got to be conduction going in and out of this little tiny slice. So we label that qx and qx plus dx. That's just like the handout. What's different from the handout is in this differential control volume, there's also some convection happening off of the surface of the fin. So there's this extra q convection term here. And now we apply our heat transfer energy balance equation, which I saw some of you were doing, which is good, right? E dot in minus E dot out plus E dot gen. Thinking about these as kind of like columns in a table. So that's a steady state problem, so this goes to 0, and there's no thermal energy generation. So we have 0 equal whatever is going in, I see Qx going in, minus all the stuff coming out. I see Qx plus dx coming out, and this convection coming out. Okay. So your next step would be to apply the Taylor series expansion for the conduction terms. So you're going to swap these two terms here for a minus derivative of qx with respect to x dx minus the convection term. And now your next step is going to be to apply your rate equations for heat transfer. So we're going to apply Fourier's law for the conduction term, and we're going to apply Newton's law of cooling for the convection term. So we have 0 as minus d dx of minus k dt dx, there's the conduction, dx, minus Newton's law of cooling is going to be h times some differential area, surface area, times t minus t infinity. Now what sometimes confuses students is this temperature here is the same as this temperature here, right? Because there's no difference in temperature between the surface and the center line or anywhere in this little tiny disk top to bottom. Right? There's only variations in the x. So those are the same temperatures. Oops, and I missed the area, didn't I? Got to get my area in there. Minus k times a.
And now we make substitutions for the areas or simplify things. So if I work on the conduction term first, right, the -1 can come out. We have constant properties, so this can come out. And we're going to say that the fin has a uniform cross-sectional area, all right? The section area doesn't change, and so the area can come out. So all those things come out. And we end up with Ka, and then the second, we end up with the derivative of temperature with respect to x. So again, we have a second derivative of temperature with respect to x. And now we need to work on this differential on this little surface area. So what's the area here for convection heat transfer? You might have to go look at your sketch of the control volume if you need some help.
Is it the pi over 4d squared times dx?
That would be true, Beth, for the section area.
Okay.
Yeah, so the section area is this one. It's like this face area. So that's A. And I agree, it's pi 4th d squared. I want to know the area on this little tiny piece right here. That's the DAS.
Is it our circumference times the dx?
That's right. So yeah, Cade said it, and then Nate also in the chat said 2 pi r dx, which is exactly right. It's the circumference times the length is the way that you can think of it. And so the circumference here is pi d, or 2 pi r. I'm actually going to write this as p dx, right, where p is the perimeter length of the fin. And that way we can actually, even though we're kind of mentally thinking of a pin fin that's circular, this will work no matter now what pin it is, as long as it's a uniform cross-section area, right? So A is the section area. And this has to be uniform. But as long as it's a uniform section area, we can apply, this could be a square fin. It works for anything, a square fin, a triangular fin. We can always represent the surface area as the perimeter times the length, right? So when I make that substitution, I'll have P dx times t minus t infinity. And now I can see that I have a common dx in both terms. So I can divide both sides of the equation by dx. Something that's, I'd say, a common misconception and easy to not kind of see initially, that's confusing, is notice that I use the same variable for the temperature in Fourier's law as in Newton's law of cooling. Right? Even though Newton's law of cooling needs a surface temperature, right? And Fourier's law needs the temperature in the solid. But remember, we convinced ourselves the BO number is much, much less than 1. It's less than 0.1. And so there is no difference between the temperature at the surface of the fin and its center line. So these are the same temperature, yeah? It's the same temperature in both places. So it's just one temperature as a function of x. Make sense? Okay, all I'm gonna do now is I'm gonna divide both sides of the equation by Ka. So I have 0 equal d squared t dx squared minus hp over Ka times t minus t infinity. And that would be, for this particular problem, this is our governing differential equation, ordinary differential equation if you want to add that. So it's our governing ODE. It's ordinary because there's no second independent variable. All we need for the independent variable is x. So this is actually simpler, right, than the equation you got for the homework due on Wednesday last week. But it looks similar, hopefully, because we also had convection off the surface in that problem. Okay, so it's going to be handy to recast this equation in it's kind of like a partially non-dimensional form. Right? I call it the relative temperature form. So we're going to define two new variables. And the reason that we're going to do this is because it's going to make the solution more general. We can make it work for any type of problem much more easily. So we're going to define what's called the relative temperature theta. And it's defined as the temperature anywhere in the fin relative to the fluid temperature. Okay. And then we're also going to define a variable m. Technically, I'm going to say m squared, but m squared is going to be this ratio of h times the perimeter of the fin relative to the thermal conductivity times the area, right? So if, as a reminder, you could just say like m is actually the square root of that stuff, but m squared is going to be hp over Ka. And so if we take those definitions and we substitute them into the governing differential equation, right, it takes on a new form. And to do that, we have to check. So like our governing differential equation has d squared t dx squared in it, yeah? So we have a d squared t dx squared in the governing ODE. So the question is, how does that relate, right, to something with theta in it? So the way that I think of that is I just take the derivative of this new variable theta with respect to x and see what happens. Actually, the second derivative, right? So I say like d second derivative of theta, right? This equation theta equal t minus t infinity. So what I see is like I have a second derivative of theta with respect to x squared. I get a second derivative of t with respect to x squared. And then the t infinity is just a constant, right? So it just is 0. In fact, it's 0 whether it's second derivative or first derivative. So there's a right? What we just exposed is the relationship between the temperature gradient and the relative temperature gradient as a way to think about this. So it's also true, right, that d theta dx is equal to dt dx. Right, so now we're going to take those definitions and we're going to put them in, right, to the substitute into the governing differential equation. Substitute into ODE. And we'll get that the new form is the second derivative of the relative temperature with respect to x minus m squared theta is equal to 0. All right. This form of a governing differential equation is pretty famous, and maybe you even recognize it from Math 270. My guess is that when you got to ODEs, you've seen this form of an ODE before. Am I right or am I wrong? Does it look familiar? Okay, I think when you see how to tackle this, for solving it, maybe you'll see it. So this should be like a recall how to solve. So be a nice little reminder to show that, you know, your differential equations course was not a complete waste of your time. So we have a form of the equation that looks like this. It's like A, this is more of a diff-EQ form, A plus B first derivative plus C equal 0, right? This is a second order linear homogeneous form of the equation. Yeah, does that ring a bell? So we need to use what's called the characteristic equation to solve. So the characteristic equation, it's like you take the coefficients, right? And it's like AR squared plus BR plus CR equals 0. And this is a quadratic equation. Does this kind of sound familiar, like you did this before? So in our particular case then, when you look at our governing differential equation for the fin, A is equal to 1, right? We don't have a first derivative in our governing differential equation, and C is equal to m squared. You see that? Like all I'm doing is I'm just comparing this form of it to what we had before. So if I take those and I put them in over there, right, what I see then is I have r squared minus m squared is equal to 0. So that means the characteristic variable r is equal to m squared. And that means that r is equal to plus or minus m. Yeah, it can be plus or minus m. So there are two real roots, right, to the characteristic equation. And that means that you always have a particular form of the general solution, right? So theta is going to equal C1 times e to the mx plus C2 times e to the minus mx. Is that, hopefully that's not, hopefully you're not thinking like, oh, I've never seen that before. I've never seen any of that stuff before, right? So this is our general solution. So you can tell just from the general solution, what kind of temperature changes do we, like, how do we expect the temperature to change along the axis of the fin? Is it going to be a linear change, or is it going to be a polynomial change or an exponential change? Oh, I'm sorry, Leah, I didn't see your, wouldn't it just be C and not CR? Oh yeah, thanks, Leah. Oh yeah, good call. Leah said right here, I put a CR, it shouldn't be CR. Thanks, good catch. Yeah, because I need a quadratic equation for the characteristic equation. So yeah, answer my question, is it going to be a linear change along the fin? Going to be polynomial? Yeah, Aaron's right. It's going to be exponential, right? Because we've got exponential functions here with x in them. So we're expecting some kind of an exponential change along the fin length. So I can almost kind of, just from looking at the general solution, kind of almost start to just visualize in my head how the temperature is going to change from the base. It should go look something like that, right? It's not going to look linear. It's going to look kind of curvy down. It's going to, you know, change more rapidly at the beginning and then decay off. Okay. All right, so in order to get to the particular solutions, right, we need boundary conditions. And so here are the boundary conditions that we'll have on these extended surfaces. So the one we already defined, right, and it'll always have this boundary condition, and that's that the temperature at the base is a known value, TB, right? So in our relative temperature thing, that means that theta at x equals 0 is equal to what we'll call theta b, because that's just TB minus T infinity, right? So that's we have a known temperature condition at the base, right? The second boundary condition, it's a second order differential equation, so there's got to be 2 boundary conditions. We'll have 4 possible cases. Let's see if I remember these from the table. A, B, C, D, okay? We'll start with the one on D at first, right? This is called an infinite fin boundary condition. So we're going to say that L goes off to infinity, right? And that means that T, right, if the fin is infinitely long, eventually it's going to come to what temperature? Okay, yeah, good. We've got a couple of answers. I'm seeing T infinity. Beth said 0. Beth is thinking about the relative temperature. She's right about the relative temperature. Yeah, T is going to go to T infinity, or the way Beth was thinking about it, that means theta, which is equal to, not B, theta, which is equal to T minus T infinity, is going to go to 0. Right, exactly right, okay. So the other 3 possible conditions we have, this is called the tip condition, okay. Let's kind of think of the table. Okay, so we have a convection tip condition, an adiabatic tip condition, and a known temperature tip condition, right? So the convection condition, we would say, okay, well, the flux out at L is equal to H times theta at L, because there's convection off of there, right? And from a surface energy balance, we could say that's got to be equal to minus K times d theta, right, dx at x equal L. Because I've already convinced you that dt dx and d theta dx are the same, right? So this would be our convection boundary condition. The adiabatic boundary condition, we would say, well, there's no heat transfer, right, at x equal L, which means what for d theta dx and dt dx at x equal L? Goes to 0, right, Leah, that's right, right? So adiabatic, we always have flat temperature lines. And then the known T, we would just say, well, okay, T at x equal L is equal to some temperature TL, which means that we'll just have theta at x equal L is equal to some known relative temperature theta L. So these are the 4 types of conditions that we can have. Okay, because it's so easy to get the solution for the infinite fin case, I want to do it quick, right? So let's just get the particular solution for the infinite fin case. So, and then we'll look at the solutions for the other cases. So from boundary condition number 1, right, we know that the relative temperature at the base is a known value, right? It's theta b, and that's got to be C1 e to the m0, because x is equal to 0, plus C2 e to the minus m0. So what's e to the 0? What's anything to the 0? Power. Oh, sorry, Aaron. Yeah, Leah, right. You're right. It's 1. Aaron, your question is why do you use the conduction equation for the Yeah, remember. So Aaron asked a question about this convection. I'm linking the 2, right? So for our mixed boundary conditions, we're linking the convection and the conduction at the tip. So this is Newton's law of cooling, right? It's H times the temperature difference, and this is Fourier's law. We're linking the 2 together, Aaron. Does that answer your question? Yep, good. Okay, so So our first boundary condition just says that, okay, if we add the two constants, they got to add up to be theta b. So now we apply our second boundary condition. And our second boundary condition is like a limit. So we're saying the limit, in the limit, as x goes to infinity, right? What's happening to our equation, theta equals c1e to the mx plus c2e to the minus mx. So what do we anticipate? We already know what we're gonna, like, we want this, right, to go to 0. We convinced ourselves of that on the last slide. We said, look, if the fin is infinite, right, eventually it's gonna take on the temperature of the fluid. So we want theta to go to 0. What's happening to e to the mx as x gets big? What happens to the exponential function as x gets big when it's the plus here? Yeah, infinite. Yeah, that's right, Leah and Aaron. Yeah, infinitely big, right? So this is going off to infinity. That's bad, right? We don't want something to go off to infinity. And when we put a minus there, it goes down to 0, right? It decays down to 0. So this term behaves the way we want, and this one doesn't. So we don't want to include this one. So we just say, okay, look, we can't let C1 be finite. C1 has to be 0, or else we're going to screw up what we want to have happen in the boundary. And then if C1 is equal to 0, that means that C2 must be equal to theta b. So then our solution becomes theta b e to the minus mx, okay? Or you're going to see in this table I'm going to show you, theta over theta b is minus e to the mx. It's kind of, or e to the minus mx, it's kind of an easy case to work. Okay, that was a little bit of math to for those of you that like it. Okay, so a little bit of diff-EQ work. So in the end, all right, the solutions to this governing differential equation are done for you in the book, and they're tabulated in this table 3.4. This is a really important table, and I would probably in my notes write, you know, we got the solution for the infinite fin case. You can see it right here, sitting in the table. The solutions for the other, the particular solutions for the other 3 possible tip conditions are in table 3.4. Like, you just want to make a note, like, I need to go to table 3.4. I don't ever have to try to solve this, get these particular solutions on my own. I just need to go to table 3.4. Okay.
Do you know what page that's on in our book?
That is a great question. I'm not sure who asked it. Could have been Haley or Rachel, or maybe Abby, I'm not sure. It is on page 161.
Thank you.
You bet. Yep. Okay, so a couple of things to point out. So about the table that'll be helpful to you. One, it reminds you about the definitions of the relative temperature and m squared. See that? So I used A, the book uses A sub C for the section area, or the cross-sectional area of the fin. It also reminds you about boundary condition 1, right, which is right here. It says the boundary at the base, we know the temperature. It's given by this. There's this other thing here, M, which is going to show up I'll show you in the 3rd column. But you can think about this as almost like a heat transfer rate. Okay, so the units on this M are going to be in watts or in BTU per hour. It's kind of important to if you just have that in your head, that'll help you check your calculations a little bit. Okay, so you shouldn't end up with a power, a thermal power. Okay, in column 2 gives you the temperature distribution, but it gives you like kind of in this case, a dimensionless temperature distribution. Yeah, what it's really giving you is theta over theta b is equal to some function. So we derived that function for the infinite fin case. So if you are ever asked in a problem to plot, right, or to comment on the temperature distribution, the way that you use this second column is you take the thing that's sitting in the column and you say, this is the function of x that has to go in here. So if I want to plot t, I just have to solve this for t, right? Because this is like t minus t infinity over tb minus t infinity. So if I'm solving that for t, it's like, it's just saying take tb minus t infinity, which is just a constant number, multiply it everywhere on the function, and then add t infinity, and you get the temperature distribution. Okay, makes sense how to use that column? And then the last column, the third column, gives you the fin heat transfer rate. So if you want to know what's the rate of heat transfer through the fin, that's what QF means. So fin heat transfer, you just go to this third column. And if you notice, it's not a function of x. So this is already like, it's already done the evaluation of Fourier's law at the base, right? So if one way to do it, like you have, we know the temperature distribution now, right? We can put that into Fourier's law and get Q through the base of the fin. Or you can think about this as integrating the convection over all of the surface of the fin. Those must be the same, right? Because what goes in must come out. So you can just go right here and just evaluate these things. And this is where the M shows up. And notice that in the infinite fin case, right, the heat transfer rate is just the value of this parameter M. And the other three cases just modify that M, right, by multiplying it by stuff. The final thing to note here in the table is do not be confused. These are not trigonometric sines and cosines, right? This is a special type of function called a hyperbolic sine, cosine, or hyperbolic tangent. Okay, so this tan h, cos h, and sine h are not trigonometric. So don't use cos on your calculator. You have to go find in your calculator the hyperbolic functions. You should be able to like do a search for these. Your scientific calculator most definitely has them, okay? MATLAB is pretty handy in that it just automatically knows, right? So if I type like cos h of 2, it gives me an answer. But if I type cos of 2, I get a completely different answer because these are two different things, okay? This is a really common mistake though. So something that maybe to write down to remind yourself, like this is a hyperbolic cosine, not a trigonometric cosine.